Alright gang, here we go. This is for Chem 2, Unit 8, talking about colligative properties here. This will be kind of a beefy part here. Gonna do some, some thinking and then some math. Should be a fun time. Alright, colligative properties. Alright, colligative properties are specific physical properties that change depending on the quantity of the solute particles that are dissolved in it. They don't really depend on the identity, they depend on just how many individual particles have been dissolved in your solution. And these are the colligative properties we're going to focus on. Okay, so the first up is vapor pressure, and we talked a lot about vapor pressure a couple of videos ago, and we showed how the whatever you're looking at, whatever solvent or liquid you're looking at, it's always going to be every once in a while you're just going to have enough kinetic energy that one molecule or two molecules or three molecules are going to be able to become a vapor. And over time, because if you have an open container, everything's going to try to escape, and eventually everything will evaporate, right? And you know that if you pour water over your kitchen table, eventually it'll all evaporate. Okay, even though it didn't boil, right? Your table's not an oven; it's not boiling, hopefully. Okay, but eventually it'll all escape, and because of reaching thermal equilibrium and all that stuff. But anyway, specifically, vapor pressure gets lowered when you start dissolving additional things in there. Okay, so what happens is that the solute-solvent intermolecular attractions makes it harder for the solvent to escape. It increases those attractions between each other. Okay, and so it keeps the solvent in solution, so it can't escape as easily. So whenever we add a solute, okay, to our solution, then the solvent's vapor pressure goes down. Okay, and they kind of show it here. You've got only solvent, you add some solute here, and it's going to interrupt these, or it's going to increase these intermolecular forces. It's going to add this solute-solvent interaction here, and then you're going to have this equilibrium being reestablished, and notice that we have a lower vapor pressure. All right, this vapor pressure can be determined by using Raoult's law. Okay, Raoult's law states that the pressure of the solution, okay, the pressure of the solution is equal to the mole fraction of the solvent times the pressure of the partial pressure of the solvent. Okay, so the vapor pressure of a volatile solvent over the solution is the product of the mole fraction of the solvent times the vapor pressure of the pure solvent. Okay, and so when we have an ideal solution, and the ideal solution is just kind of a solution that kind of obeys all of our simple rules that we've established. It is assumed that each mixture or each substance will follow Raoult's law while in the mixture. Right? So pressure of the solution equals mole fraction times the pressure of the solvent. So let's try one here. The vapor pressure of benzene is 100 torr at 26.1 degrees Celsius, assuming Raoult's law is obeyed. How many moles of non-volatile solute must be added to 100 milliliters of benzene to decrease its vapor pressure by 10% at 26.1 degrees Celsius? The density of benzene is that. Okay. So we know that we're going to use Raoult's law here, and it says Raoult's law, which is helpful. And we know Raoult's law has mole fraction. So the first thing we need to do is figure out what the mole fraction is. Okay, or at least we need to know how many moles of solvent we're using here. Okay, so the first step here is we're going to take our 100 milliliters of benzene, 100.0 milliliters, and we got to convert this to moles. All right, so this is our C6H6. All right. And we're going to move pretty fast through these things because there's a lot of math problems we have to do. So we're going to do 100.0 milliliters of benzene, and then we're going to go to milliliters down here, milliliters, and we're going to go to grams, and it says this is the ratio of grams per milliliter. And remember, centimeter cubed is the same as milliliters, so we got 0.8765 grams for every 1 centimeter cubed. And then we're going to go from grams to the moles. So we're going to put grams of benzene, moles of benzene. All right, and I've already calculated this molar mass. It was 78.11 grams per mole. All right, so this will give us our molar mass. So we take 100 times 0.8765 divided by 78.11. All right, we get 1.12 moles. All right, so 1.12 moles of our C6H6. All right. So essentially what we want, if you really think about what's going on here, is we want our guy, we want it to be at 90, or we want it to decrease by 10%. Well, if it decreases by 10%, then it would be at 90 torr. Okay, and 90 torr would be at 90% of what we want to be. So really, if we want to decrease by 90%, really we just need to decrease our pressure by 90. So if we set 0.9 equal to our mole fraction, we should be good, right? If 0.9 is equal to our mole fraction, then that's exactly what we want to solve for. So the 0.9, well, that would be, so the mole fraction, so this would be the moles of solvent, right? Or this is the mole fraction of solvent, right? Solvent, maybe we'll note that here, that we're solving for. So this would be the 1.12 moles right here over, okay, the total number of moles. So that'd be the 1.12 plus whatever our x value is here, right? And that x value is the number of moles of solute that we need to add. Okay, and then from here it's just a algebra to solve for this. So there's several ways we could solve for it, but I don't know. Let's do something fun. Let's flip both sides upside down. So we'll take the inverse of both sides, right? So we have 1 over 0.9 is equal to 1.12 plus x divided by 1.12. All right, multiply both sides by 1.12 and then subtract by 1.12, and our x is equal to, all right, so 0.9 inverse times 1.12, and then we'll minus 1.12, and we get 0.124. Oh shoot! Spoilers. Okay, put it on the space bar. All right, 0.124. Let's see, what were our options? How many sig figs do we want on this thing? It says 4 sig figs, and that's really the only number we used. Everything else, so it would be 1.24, and I got 1.12444, right, is what I got when I did the math here. So anyway, so that's the moles of solute that we need to add. Okay, and this is closest to this value here, C. Okay, not too bad. Okay, and we could do that one, but it's essentially the same thing. All right, boiling point elevation. So remember when we talked about boiling point, we reach boiling point because our vapor pressure, remember the boiling is when the vapor pressure is equal to the atmospheric pressure. That's the definition of boiling point. Well, if our vapor pressure lowers, okay, that means it's going to be harder to reach our atmospheric pressure, right? Because when we just established that adding a solute makes our vapor pressure go down. So if we're lowering our vapor pressure, then it must be harder to reach our boiling to reach that point where vapor pressure equals atmospheric pressure, so therefore it's going to take more energy, so therefore we're going to be at a higher temperature. Okay, so boiling point goes up when we add a solute. All right, and so this is essentially why, like, if you've ever heard like spaghetti cooks faster if you add a little bit of salt to your boiling water, the spaghetti will actually cook faster because you're making the solution be at a higher temperature. Remember, when a solution, or when anything is changing phases, okay, the temperature cannot change until it's completely made it to the next phase. So if you're sitting here in Kansas and you're boiling water, it boils at probably like 99 and change, okay, degrees Celsius. If you add salt to it, it'll raise that boiling point. It might boil at like 100 or 100 and change. Okay, so but because it's at a higher temperature, it's going to be getting more energy to those noodles, and then the noodles will cook. All right, so it'll require higher temperature. So here you've got this phase diagram, pressure and temperature. All right, and notice here, so this is at 1 atmosphere. This is your normal boiling point, is when you make from the liquid to the gas stage. All right, and so notice that by adding the solute, this black line was the normal. Okay, the normal phase diagram. Adding the solute, it makes this change, right? It moves it from this to this, and so this value here is defined as the change in the boiling point, because this was the boiling point of the pure solvent, all right, and this was the boiling point of the new solution. Okay, and so this was your boiling point elevation. You might also notice that on the opposite side, that these phase diagram goes the opposite direction, right? We go from here okay, to the left here. And so then we get a freezing point depression. It goes lower. And so essentially the reason this happens is because in order for crystallization to happen, those intermolecular forces have to, take over the kinetic energy, okay, or be stronger than the kinetic energy available for the molecules, so it crystallizes, it forms those lattice patterns, okay? And so when you start to crystallize, your molecules start to line themselves up. Well, if there's a bunch of things in the way, they can't line themselves up, so you have to take away extra energy in order for them to boil, or in order for them to be able to reach that point at which you can have this this arrangement, okay? And so you get this guy going on like this, and so you get a lower freezing point, okay, as you add solute. All right, so again, you've got this lowering of the vapor pressure, okay, and then your freezing point goes down. So we have boiling point elevation and freezing point depression. All right, those are important. Boiling point elevation and freezing point depression. All right, the change in the temperature is directly proportional to molality. Remember, we talked about using molality because it's in moles, okay, of the solute, moles of the solute per kilogram of the solvent. Okay, remember that. So that's your molality. Okay, now these are the formulas. This is the change in boiling point, and this is the change in freezing point. All right, these I values is called the Van't Hoff factor. Van't Hoff factor. All right, and it's literally equal to the number of particles a substance becomes when it dissolves. So you have to pay attention. If you're dissolving an ion, you got to figure out how many ions it's breaking up into. If you're dissolving an organic compound, then it's just going to stay as itself. All right, and so your I value is your Van't Hoff factor. It's always going to be a whole number. Okay, it's always an integer. Now your K values here are your constants for either boiling, and obviously if you're doing the change in boiling, then you should use this guy for your boiling, your KB for your change in boiling point, and KF for your change in freezing point. All right. The units for your K values are always in degrees Celsius per molal. Okay, right here it's degrees Celsius per molal. All right, and so then to get rid of the molal part, you multiply it by the molality of your solution with the solute. All right, and so you can kind of get an idea. Here's our boiling points and freezing points, and then notice that you've got different KB values. Kind of depend, there's not really a huge pattern to these things. They just kind of depend upon, how it interacts with solutes that are added. Okay, yeah. Should be fun. So IKBM, and notice that the boiling point is a positive value, right? It's positive out front because we're raising the boiling point, and the change in freezing point is a negative value because we're lowering the freezing point, right? That makes sense. Freezing point elevation, or boiling point elevation, freezing point depression. All right. All right. We're gonna skip this and do a practice problem, maybe. All right. It says, which aqueous solution will have the lowest freezing point? Well, remember, these are all aqueous solutions, so that means the base starting freezing point is at 0 degrees Celsius. Now, we can't necessarily calculate, well, we could actually calculate the freezing point for each of these solutions, because we could go back to that table, find the KF value for water, and then just multiply it by the molality, and then also the Van't Hoff factor. But essentially, all we have to do here to say, and we could do this for all 6 of them, or 5 of them, 1, 2, 3, 4, 5, and figure out what's going on. But then the other way we could do it that would save us a little bit of time is if we could just figure out which one has the greatest molality of just particles broken up, then that would be the one that has the biggest change. So A here, the Van't Hoff factor for calcium chloride, this is going to form 3 ions, 1 calcium and 2 chlorines. So its Van't Hoff factor is 3. Okay, so there will be 3 times that value there, number of molal particles. So that would be 0.15 molal of particles, right? And then for B here, sodium chloride breaks up into 2 particles, so it would have 0.30 molal of particles. All right, C would have, there's 2, right, hydrogen and then chloride ions, so those would break up, and so you'd get 0.20 molal. All right, and then you got D here. D, again breaks up into two pieces. You got your acetate, and then that hydrogen will break off. So you get 0.1 molal. Alright, and then finally your E, well, this is glucose, and so it won't break up at all because it's organic, and so you get 0.20 molal. Alright, so the one that has the biggest molality is going to be the one that provides the biggest change, and so that's B. That's the 0.3 molal. Alright, so there's your answer there. Alright, let's try exercise dose. Okay, it says, referring to table 13.3, calculate the freezing point of a solution containing 0.6 kilograms of chloroform, that's exciting, and 42 grams of eucalyptol. Alright, so the chloroform is going to be our solvent. This is our solvent, and and we know it's our solvent because there's more of it. All right, and then the eucalyptol will be the solute here. Okay, and so we want to calculate the freezing point depression, or the new freezing point, so that we can calculate the change in the freezing point. Well, that's TF is equal to negative IKF times the molality. All right, so the I value here would be just how many pieces it's breaking up into. Well, this is organic, so it doesn't break up into anything. It's just one piece. All right, so that'd be -1. All right, so that's easy. The KF value, well, then since the chloroform is our solvent, we'll find chloroform on the list here. That's CHCl3. All right, and its KF value is 4.68. All right, 4.68 degrees Celsius per molal. All right, and then finally we need the molality of our solution. All right, so this is kind of where the rubber meets the road, if you remember how to do molality. So molality is equal to moles of solute. Oh my goodness, solute divided by kilograms of solvent. All right, so we got to find the moles of solute first. All right, I'm running out of space, but that's all right. Moles of solute, well, we had 42.0 grams of C10H18O. All right, and we got to convert that to moles, so we'll put grams in the bottom, moles in the top, 1, and then we got to add up all this thing. So we got 10 carbon, so 10 times 12.01 plus 18 times 1.01 plus 16, and we get 154.28 grams. All right, 154.28 grams. All right, so we'll take our 42 divided by that guy, so we get 0.2722 moles. All right, so that's the top part here, 0.2722. All right, and then we need the kilograms of solvent. Well, that's just right here. That's just the 0.600 kilograms. All right, so we'll divide that by our 0.6. We get 0.4537 molal. All right, so we'll plug that guy in here, 0.4537 molal. All right, so everything will cancel out. So we have essentially we get negative 4.68 times our answer to the previous question, and so therefore our temperature will go down by negative 2.123 degrees Celsius, right? But that's not quite what the answer asks us. That's the change in our freezing point. So our freezing point is going to go from negative 63.5, because that's the normal freezing point, and it's going to go down an additional that value there. So we're going to add those two values here. So we're going to add in negative 63.5. All right, minus 63.5. And so our answer becomes negative 65.6 degrees Celsius. So that's going to be our new freezing point there. All right, not too bad. The next one here, osmosis, says some substances form semi-permeable membranes, allowing smaller particles to pass through, but blocking larger particles. Okay, the net movement of solvent particles from solution of low concentration to high concentration of solute across semi-permeable membrane is called osmosis. The applied pressure to stop it is called osmotic pressure. So essentially, so look here, we've got a bunch of water and a bunch of solute particles, and then a semi-permeable membrane. So it's semi-permeable because it'll let water through, but not the solute particles. So because this comes through the water, because this has very, very low concentration of solute, and this has very, very high concentration of solute, the water is going to flow from the left to the right. All right, and so we end up with this lopsidedness. This was, where we initially started, and then we allowed transition to occur, and then and so we reach equilibrium. Once it's reached equilibrium, we can measure the osmotic pressure by pushing down on one side and measuring how much pressure it took. Now it turns out that adding solute to it will actually change our osmotic pressure. Okay, and so this is the formula. This capital Pi symbol is this symbol for osmotic pressure our textbook uses, and the formula is this guy here: I times the molarity times the R value, remember, and that makes sense because we're talking about pressure, okay, times the temperature, okay, and because our R value's in Kelvin, then our temperature also needs to be in Kelvin, so watch out for that, because before, when we talk about freezing point, depression, and elevation, primarily we just worry about degrees Celsius, but here we need to make sure we're in Kelvin, all right? So this is an important thought here. If two solutions separated by a semi-permeable membrane have the same osmotic pressure, then no osmosis will occur. They won't go from one side or the other. All right. Types of solutions. All right. These are just words that you need to be familiar with. An isotonic solution is a solution that has the same osmotic pressure on one side, okay, versus the other. So the solvent passes the membrane at the same rate. Essentially, you've reached equilibrium. All right. We'll kind of make that so you've reached equilibrium. Okay. Hypotonic solutions is when you have a lower osmotic pressure. All right, so your solvent actually leaves the solution at the higher rate than it enters. Okay, so this is hypotonic. And then hypertonic solutions is when you have a higher osmotic pressure and your solvent will enter the solution at a higher rate than it leaves with. Okay, so hypotonic, hypertonic. All right. Oops, I think I put these slides out of order. Let's go back here real quick. I did. I put them in. Let's look at this slide real quick, and then we'll go back and do some math here. Okay, so in a good application of this is is in the medical field. All right, when they're adding. So if you've ever had an IV or been to the hospital or seen somebody else with an IV, you know that they don't just put straight water into your blood. They put in a special saline solution, which means that it's got a certain amount of salt dissolved in it. And the reason it has to have that certain amount of salt is because it needs to make sure that you haven't changed the molarity and the concentrations in your bloodstream, okay? Because your red blood cells are a semi-permeable membrane, it will let solute come in or out, all right, but it won't let the individual particles. So the only way it can reach equilibrium and change concentrations is by adding in or taking away solvent, all right, from inside of those red blood cells. And so if you have if your osmotic pressure is too high, okay, then you'll have too high, you'll have a hypertonic solution, and so all of your solvent will leave your red blood cells, and it'll shrivel up and die, and they call that crenation. Whoops, my pen's gone. All right, and then hypotonic solutions is the opposite, and solvent will go in until the red blood cells actually burst, and that's called hemolysis. All right, and so that's also no good. All right. So anyway, so be familiar with those things. So that's why they have to use isotonic intravenous solutions or IV solutions. All right, kind of interesting thought here. All right, let's go back here. You're seeing behind the curtain a little bit here. All right, where's my little button? Oh, okay. All right, practice lecture. Which of the following will raise the osmotic pressure of a solution? All right. Well, the easiest way to do these things is just to look at the formula here. You got a capital Pi is equal to IMRT. All right, so these are the things that affect your osmotic pressure. So, decreasing solute concentration. Well, if we decrease solute concentration, that means your molarity will go down. That means that your osmotic pressure goes down. It's not that one. Decreasing temperature, same idea. The T goes down. Adding more solvent. Well, if we add more solvent, then that makes our molarity smaller, right? Because that would, the moles on top would stay the same, but the denominator would be getting bigger. So the molarity would go down. So that would also decrease the osmotic pressure. Increasing the temperature, though, for sure, would raise the osmotic pressure because we're raising that T value. All right. What is the osmotic pressure in atmospheres, of this guy here? Cool. So osmotic pressure is equal to I m r t. All right, so it looks like we just get a plug and chug here. Our I value, that's our Hoff factor. Well, that's just 1 because this guy's is just 1 sucrose. So that's nice. So it's 1. And then the molarity, well, they give that to us. We don't even have to calculate that. So this is coming along really nicely. All right, R value, well, if it's in atmospheres, that means we get to use our standard 0.0821 R value. And then our temperature, well, that's 20 degrees Celsius. They almost got us. Remember, we got to convert that to Kelvin. So that would be 293 Kelvin. All right, so that'd be 293. Okay. All right, so the osmotic pressure is equal to 0.002 times 0.0821 times 293. And so our osmotic pressure would be equal to 0.048. How many sig figs? Dose sig figs, 0.048, and the units are pressure, so it'd just be atmospheres. Okay, not too bad. Now this is where life gets a lot more exciting here. Okay, we can actually use molar mass, or the freezing point depression and boiling point elevation, in order to figure out the identity of an unknown, and we can use it to find the molar mass. Okay, and so let's walk through. We're going to walk through this one that they do here, and then we're going to do one ourselves. All right, so it says a solution of unknown non-volatile non-electrolyte, all right, was prepared by dissolving 0.250 grams of the substance in 40 grams of carbon tetrachloride, CCl4. The boiling point of the ending result was 0.357 degrees higher than that of the pure solvent. Calculate the molar mass. All right, so then they say our goal is to calculate the molar mass of the solute based on the knowledge of the boiling point elevation of its solution, and the change in boiling point is that, and the mass of the solute is solvent. All right, we can find the, and it says we found the Kb is this guy here, 5.02. All right. So we've got CCl4, so there's our 5.02 normal boiling point, but we don't really need this because we've already got the change in P, or a change in delta P, TB. So here's our plan. We can use this equation to calculate the molality of the solution, all right? And that'd be easy because we have that guy, we know the Van Hoff factor, we have the Kb, so we can find the TB, the molality, really easily. And then it says use the molality and the quantity of solvent to calculate the number of moles. Finally, the molar mass equals, and this is the part where most people get thrown off, the molar mass of the solute equals the number of grams per mole. So we divide the number of grams, so that's the thing we started with, by the number of moles we have just calculated. Okay. So let's walk through it. So first, they find their molality by using their formula here. Okay, oops. All right, so their molality is equal to this. The change over the IK, I is 1. There's your K, and you get this as your molality. All right. Then they're going to use the starting, this value here. Remember, this is in moles per kilogram, right? So they use that guy down here, and by multiplying it by the kilograms of the solvent that they had, they can find out how many moles of solute, right? So this here is their moles of solute. All right, that's not too bad. And then, so the molar mass of the solute would simply be the number of grams per that they started with, 0.250, divided by the number of moles that it took, which was, so then they found that the molar mass of their unknown was 88.0 grams per mole. All right, let's try one ourselves. So it says a mysterious white powder could be powdered sugar, cocaine, codeine, norepinephrine, or fructose. All right, so, ooh. All right. When 80 milligrams of the powder is dissolved in 1.50 milliliters of ethanol, the freezing point is lowered to this value here. What is the identity of the powder? All right. So first thing we need to do is we need to find the density, or we need the density. We need to find the molality, right? So remember that your delta T, so this is freezing point, so delta TF would be equal to negative I KF molality. okay? And we're looking for molality, so our molality would be equal to delta TF over negative IKF. All right. Anytime we have a change in, it's always final minus initial. So it'd be the temperature, the final temperature minus the initial temperature. Okay, and I'm just going to use 1 and 2 to keep track of it for this guy here. And then it would be negative IKF. Alright, so now we can just start plugging guys in here. So the final temperature, well, the final temperature was negative 115.5. Alright, so negative 115.5. And then our initial temperature, well, that was what the normal freezing point is, so that'd be the negative 114.6. So we'll add in the negative 114.6. Alright. And then we'll divide this by our negative I value, and I value because all these guys are, or this is nice. If these weren't, if some of them were molecular, some of them were ionic, would be in trouble, but they're all molecular. So they all have a von Hoff factor of 1, and then the KF value is 1.99. Alright, it says it right here. Alright, so what do we get? So we get negative 115.5 minus a negative 114.6 divided by negative 1.99. Alright, so we get a temperature change of negative, or positive, sorry, positive 0.4523. Alright. Oh, no, that's not the temperature change. That is the molality. Oh, okay. So that's the molality. Alright, now, so what we need to do is we're going to use this to figure out how many moles we had, right? Because the molality is equal to moles per kilogram. All right, so let's see. So this is really saying we have 0.4523 moles of whatever our solute is, okay, divided by the kilograms, and so it's a ratio of 1 kilogram of the solvent. Alright, so if we can get rid of the kilograms of the solvent, we'd be set. Now the problem is they don't tell us the mass directly of the solvent we use. They just tell us that we have 1.50 milliliters of ethanol. So we got to figure out the kilograms. So let's do, we got to use the density here. So 1.50 milliliters. Alright, we're going to convert that to kilograms. So the first step was we're going to put milliliters in the bottom, grams in the top. We use this guy here. Remember, centimeters cubed equals milliliters. So we have 0.789 grams for every 1 milliliter. And then we got to get it to kilograms because that's what's in our molality here. So we have 1,000 grams for every 1 kilogram. All right. So we take 1.5 times 0.789 divided by 1,000. All right, and we get 0.00118. 4. All right, so that is our kilograms. So we'll multiply this guy by 0.00184 kilograms. All right, so times 0.452. All right, and I got, let's see, 5.352 times 10 to the minus fourth. And so this is our moles of solute. Now remember, our molar mass is in grams per mole, so we're halfway there. All right. So the molar mass, we'll say that's capital and big M here, all right, is equal to the grams of the solute over the moles of the solute. All right. Well, we know the grams was 80 milligrams, so that would be divided by 1,000, so 0.08 grams. All right. And then the moles we just found was 5.352 times 10 to the minus fourth moles. All right, so we'll say 0.08 divided by our answer, and I got 150. How many sig figs? Just 2, because that's, well, really only just 1, but that's not going to help us. I think we're going to add a decimal because I think we need it. 150 grams per mole. All right. 150 grams per mole. All right, so now that would be the molar mass of our thing that we're looking for. But we've got to identify which one it is. So 150. Well, there's some of them we can just throw out right away. Like this thing, friggin' 11 oxygens. That's already 10 oxygens would get us over 150 by a lot, and then adding another one plus 12, so that's right out. Cocaine might be close. I don't know. It's probably, we'll kick that one out too. This guy's definitely out too. Let's see. This is gonna be really close. All right, and this one might also be close. But if you pay attention to biology, you probably already know. So let's check norepinephrine. So we'll say 8 times 12.01 plus 11 times 1.01 plus 14.07 plus or 14.01 plus 32. Yeah, 153.2. So norepinephrine weighs 153.2 grams per mole. Alright, and let's try fructose just for grins. 12.01 plus 12 times 1.01 plus 6 times 16. You get 180. Yeah. As I expected. Alright, norepinephrine then. The white powder that we had would be that guy there. That's the identity. We did it. Alright. We already talked about that slide. That's it. We did it. All right. Colligative properties in the bucket. We made it. All right. So do lots of practice for those guys. They can be kind of tricky. This math here looks complicated at first, but if you just break it down to what are you trying to solve for and then solve for those things, it's really not that bad. You do need to be able to do this math in order to do our upcoming lab. All right. So make sure you get this under control. Let me know if you have any questions, and I'll see you on the flip side.